Something happened recently that shook the scientific community to its core. The James Webb Space Telescope, our most advanced eye in the cosmos, pierced deeper into space than ever before. What it discovered challenges everything we thought we knew about the universe's beginning. Ancient galaxies that shouldn't exist, structures too massive, too organized, too mature for their cosmic age. It's as if someone built a skyscraper before inventing bricks. Scientists are scrambling for answers, and what they're finding is profoundly disturbing. And one quick question: if you could witness any moment in the universe's history firsthand, which would you choose? Comment down below. I will pin the most creative answer. Now let's begin. Picture yourself standing at the edge of time itself. That's essentially what the James Webb Space Telescope allows us to do. Launched on Christmas Day 2021, this remarkable instrument orbits the Sun approximately 1 million miles from Earth. Unlike its predecessor, the Hubble Space Telescope, Webb observes primarily in infrared light. This capability proves crucial because as the universe expands, light from distant objects stretches into longer, redder wavelengths. The further away something exists, the more its light shifts toward the infrared spectrum. Webb's 18 hexagonal gold-coated mirrors work together like a cosmic time machine, gathering photons that began their journey billions of years ago. Within months of beginning operations, Webb started sending back images that left astronomers speechless. Galaxies appeared where silence should have reigned. The early universe, which models predicted would be relatively empty and simple, turned out to be bustling with complex structures. These weren't just small clumps of matter beginning to gather, these were fully formed spiral galaxies, massive elliptical systems, and structures exhibiting characteristics that should have taken billions of years to develop. Consider what we're actually seeing here. Travels at approximately 186,000 miles per second. When we observe an object 13 billion light-years away, we're seeing light that departed when the universe was merely 700 million years old. That's roughly 5% of its current age of 13.8 billion years. In cosmic terms, this represents the universe's infancy, comparable to observing a 6-month-old human baby. The standard cosmological model, refined over decades of observations and calculations, predicted what this infant universe should look like. According to the lambda-cold dark matter model, which has successfully explained countless cosmic phenomena, the early universe should contain only small, irregular proto-galaxies. These primitive structures would gradually merge over billions of years, forming the majestic spiral and elliptical galaxies we observe in our cosmic neighborhood today. Stars in these early systems should be relatively small, composed almost entirely of hydrogen and helium, since heavier elements hadn't yet been forged in sufficient quantities. But Webb's observations paint a radically different picture. Galaxies designated as JD's GS-Z13-1 and JD's GS-Z12-0 exist at distances corresponding to merely 330 million years after the Big Bang. These objects shouldn't simply be slightly more developed than expected. They appear fundamentally impossible according to current physics. Their brightness suggests they contain hundreds of millions of stars, perhaps even billions. Their structure indicates organized rotation and sophisticated gravitational interactions. Some exhibit clear spiral arms, features requiring millions of years of stable rotation to form. Even more puzzling are observations of galaxies containing what astronomers call metals, elements heavier than helium. In astronomical nomenclature, everything heavier than helium counts as a metal, including carbon, oxygen, and iron. These elements only form inside stars through nuclear fusion, then scatter into space when those stars explode as supernovae. This process requires multiple generations of stars living and dying. First-generation stars must form, live their entire lifespans, explode, and enrich the surrounding gas with heavier elements before second-generation stars can incorporate these materials. This cycle demands time, significant amounts of time. Yet Webb observes signs of metal enrichment in galaxies existing when the universe was supposedly too young for even one complete stellar generation. The situation grows more perplexing when examining the sheer number of these impossible galaxies. Webb doesn't just find one or two outliers that might represent unusual cases. Dozens of unexpectedly massive, mature galaxies populate the early universe. In January 2026, researchers announced the discovery of strange red dots in Webb's images. For years, these crimson specks puzzled scientists. New analysis reveals they're actually young black holes surrounded by dense clouds of gas, growing at furious rates as they devour their surroundings. But here's the disturbing part. These black holes are already supermassive, containing millions or even billions of times the Sun's mass, existing when the universe was less than 1 billion years old. Black hole growth follows predictable patterns. A black hole forms when a massive star collapses, typically starting with perhaps 10 to 100 times the Sun's mass. From there, it grows by accreting matter from its surroundings. However, this growth has a natural speed limit called the Eddington limit. As matter falls into a black hole, friction heats it to millions of degrees, causing it to emit intense radiation. This radiation pressure pushes against incoming matter, creating a natural brake on how quickly the black hole can grow. Even feeding continuously at the maximum rate, a stellar mass black hole shouldn't reach supermassive proportions for several billion years. Yet Webb finds supermassive black holes already in place, actively powering brilliant quasars when the cosmos was less than 700 million years old. Some of these ancient monsters contain over 1 billion solar masses. The mathematics simply doesn't work. Starting from a stellar mass black hole seed and growing at the theoretical maximum rate still doesn't provide enough time to reach these observed masses. Either our understanding of black hole formation and growth contains fundamental flaws, or these objects formed through mechanisms we haven't yet imagined. Before we continue diving deeper into these cosmic mysteries, I want to take a moment to ask for your support. If you're finding this journey through space and time fascinating, please hit that subscribe button and give this video a thumbs up. Your engagement helps this channel grow and allows me to continue exploring these incredible discoveries with you. These are genuinely exciting times for astronomy, and I want to share every new revelation as scientists uncover them. Now let's examine another disturbing discovery. Webb's observations reveal not just individual impossible galaxies, but entire cosmic structures that challenge our timeline. Astronomers discovered what they call protoclusters, regions where dozens of galaxies congregate, bound together by gravity. In our local universe, galaxy clusters represent the largest gravitationally bound structures, containing hundreds or thousands of galaxies spanning millions of light years. They form over billions of years as cosmic expansion works against gravity, slowly allowing matter in particularly dense regions to pull together. Finding protoclusters in the early universe makes sense. These would be the seeds of today's great clusters, regions where matter concentration began. But Webb observes protoclusters that appear surprisingly well developed. Some contain dozens of galaxies already interacting gravitationally, their motions synchronized in cosmic dances. The galaxies within these protoclusters aren't just randomly positioned nearby objects. They exhibit coordinated structures suggesting they've already undergone significant evolution and interaction. Consider the Great Wall, a massive structure in our relatively nearby universe discovered in 1989. This structure stretches across 500 million light-years, containing thousands of galaxies organized into a sheet-like pattern. Its formation required billions of years as dark matter's gravitational influence pulled ordinary matter along cosmic filaments, gradually building these grand structures. Yet Webb observes similar large-scale structures already taking shape when the universe was supposedly too young for such organization. Dark matter itself adds another layer to this mystery. This invisible substance, which neither emits nor absorbs light, comprises approximately 85% of all matter in the universe. We infer its existence from gravitational effects on visible matter and light. Dark matter provides the gravitational scaffolding upon which galaxies and larger structures form. Computer simulations of structure formation depend critically on dark matter's properties and distribution. These simulations, refined over decades and matching observations of the modern universe remarkably well, predict a gradual buildup of structure. Small fluctuations in density grow slowly into progressively larger structures over cosmic time. Webb's observations suggest this process occurred far more rapidly than simulations predict. Either dark matter behaves differently than we thought, or additional physics operates in the early universe that our models don't incorporate. Some physicists propose that dark matter might interact with itself through forces we haven't yet detected, potentially accelerating structure formation. Others suggest modifications to gravity itself at cosmic scales. Still others wonder whether our fundamental assumptions about the universe's expansion history need revision. The expansion history question opens particularly intriguing possibilities. We measure cosmic expansion through redshift, the stretching of light from distant objects. The further away an object, the more its light stretches toward redder wavelengths. By measuring redshift, we calculate distance and look-back time. However, this calculation depends on assumptions about how expansion rate changed over cosmic history. If the early universe expanded differently than current models assume, our distance and age calculations could be systematically wrong. Some researchers propose that the universe underwent a period of rapid expansion, followed by slower expansion in its earliest moments, different from standard predictions. This modified expansion history might provide more time than we currently calculate for structures to form. If galaxies we think existed at 700 million years actually formed at, say, 1 billion years, that additional 300 million years might resolve some tensions. However, this solution creates its own problems, potentially conflicting with other observations like the cosmic microwave background radiation. The cosmic microwave background, or CMB, represents light released when the universe was approximately 380,000 years old. At that moment, the cosmos cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. We observe this ancient light today as microwave radiation coming from all directions. Tiny temperature variations in the CMB provide a snapshot of density fluctuations in the early universe, the seeds from which all structure grew. Measurements of the CMB by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory provide exquisitely precise data about the early universe's conditions. These observations match theoretical predictions with stunning accuracy, validating our understanding of physics at that epoch. The CMB data constrains how quickly structure could form afterward. Any model attempting to explain Webb's observations must remain consistent with CMB measurements. This requirement severely limits possible solutions, eliminating many otherwise appealing ideas. Another puzzle emerges when examining the chemical composition of early galaxies. Spectroscopy, the analysis of light broken into component wavelengths, reveals which elements exist in distant objects. Different elements absorb and emit light at characteristic wavelengths, creating unique fingerprints. By analyzing these signatures, astronomers determine not just what elements are present, but in what quantities. Webb's spectrographic capabilities surpass any previous instrument. Its observations reveal surprisingly high abundances of heavy elements in some early galaxies. Remember, these elements only form through stellar nucleosynthesis, the fusion processes occurring in star cores and supernova explosions. The presence of significant quantities of carbon, oxygen, nitrogen, And even iron in galaxies less than 1 billion years old implies multiple generations of stars had already lived and died. Let's walk through the timeline required. First-generation stars composed almost entirely of primordial hydrogen and helium must form from collapsing gas clouds. The most massive of these stars live only a few million years before exploding as supernovae, scattering their fusion products into space. The enriched gas must then cool and collapse again, forming second-generation stars incorporating these heavier elements. The most massive second-generation stars also have short lifetimes, perhaps 10 to 20 million years, before they too explode, further enriching the surrounding medium. This cycle must repeat multiple times to build up substantial quantities of heavy elements. Even assuming the fastest possible stellar evolution, this process requires at least several 100 million years. Yet we observe metal-enriched galaxies that appear to have formed and evolved in timeframes potentially too short for this enrichment process to complete. Either stars in the early universe behave very differently than contemporary stars, or we're missing something fundamental about how elements disperse and incorporate into new stellar generations. One proposed explanation involves population 3 stars, a theoretical first generation of stars predicted to have been vastly more massive than typical stars today. These hypothetical giants might have contained hundreds or even thousands of solar masses, burning through their fuel in just a few million years before exploding with tremendous violence. Such explosions would rapidly enrich large volumes of space with heavy elements. However, despite extensive searching, astronomers have never definitively observed a population 3 star. Their existence remains theoretical, supported by models but not direct observation. Webb offers the best chance yet to detect these primordial giants. If they existed, some should still be visible in the most distant reaches of the observable universe. Researchers carefully analyze Webb's data, searching for the distinctive spectral signatures these massive stars would produce. So far, clear detection remains elusive. Some candidates show promise, but confirmation requires additional observations and analysis. The absence of obvious population 3 stars makes the metal enrichment puzzle even more perplexing. Temperature measurements add yet another layer to this mystery. Stars form in cold, dense regions where gravity can overcome gas pressure and pull matter together. In the modern universe, giant molecular clouds provide ideal nurseries, their temperatures hovering just a few degrees above absolute zero. But the early universe was inherently warmer. The CMB, now cooled to merely 2.7 degrees above absolute zero through cosmic expansion, was correspondingly hotter in the past. At redshift 10, corresponding to roughly 480 million years after the Big Bang, the CMB temperature was approximately 30 degrees above absolute zero. This might not sound like much, but it significantly affects star formation. Warmer gas is more turbulent, making gravitational collapse more difficult. The early universe's higher background temperature should have suppressed star formation compared to later epochs. Yet Webb observes vigorous star formation in these ancient galaxies, with some forming stars at rates comparable to or exceeding modern galaxies. This contradiction suggests either additional cooling mechanisms operated in the early universe, or star formation physics differs at high redshift in ways we don't yet understand. The sheer brightness of some early galaxies presents its own problem. Luminosity correlates with stellar mass. Brighter galaxies contain more stars. Some Webb-observed galaxies shine so brilliantly that they must contain stellar populations comparable to the Milky Way, our home galaxy containing roughly 200 billion stars. The Milky Way formed over billions of years through numerous mergers and continuous star formation. How could comparable stellar masses assemble in a fraction of that time? One possibility involves exceptionally efficient star formation. In the modern universe, only a small percentage of a galaxy's gas typically converts into stars, with the remainder remaining as interstellar medium or being expelled by stellar winds and supernovae. Perhaps early galaxies converted gas into stars with far greater efficiency, rapidly building large stellar populations. But what would cause this enhanced efficiency, and why would it decline over cosmic time to the lower efficiencies we observe today? Another consideration involves the initial mass function, abbreviated IMF, which describes the distribution of stellar masses when stars form. In our galactic neighborhood, for every massive star formed, hundreds of low-mass stars are born. Low-mass stars like red dwarfs burn their fuel slowly, living trillions of years. Massive stars burn brilliantly but briefly, living only millions of years. The IMF's shape dramatically affects a galaxy's observable properties. If early galaxies formed proportionally more massive stars than modern galaxies, they would appear much brighter for a given total stellar mass. A top-heavy IMF containing more massive stars than typical could explain some of Webb's observations. Massive stars are inherently far more luminous than low-mass stars. A single star containing 50 solar masses shines roughly 500,000 times brighter than our Sun. If early star formation favored such giants, relatively modest stellar populations could produce extraordinary luminosities. However, this solution creates problems elsewhere. Massive stars also die quickly, and their deaths should produce observable consequences. When massive stars explode as supernovae, they inject enormous amounts of energy into their surroundings, heating gas and potentially blowing it out of the galaxy entirely. If early galaxies formed predominantly massive stars, this feedback should have been intense, possibly preventing further star formation. Yet Webb observes sustained star formation in these systems, suggesting they retain sufficient gas despite potential feedback effects. Reconciling these competing factors challenges theorists. Dust adds another complication. Cosmic dust consists of tiny particles, primarily composed of carbon and silicon compounds, formed in stellar atmospheres and supernova explosions. Dust absorbs ultraviolet and visible light, re-radiating the energy as infrared radiation. Dusty galaxies appear dimmer in optical wavelengths but brighter in infrared. Webb's infrared sensitivity makes it particularly effective at detecting dust-obscured galaxies that optical telescopes might miss. Some researchers initially hoped dust might resolve the brightness problem. Perhaps early galaxies aren't as intrinsically luminous as they appear. Maybe dust obscures a substantial fraction of their light, and we're only seeing part of their true brightness. However, detailed analysis suggests dust cannot fully explain the observations. The spectral energy distributions, the way brightness varies across different wavelengths, don't match expectations for heavily dust-obscured galaxies. While dust certainly exists in these systems, it doesn't appear abundant enough to account for the brightness discrepancy. Furthermore, dust presence itself is problematic. As mentioned earlier, dust forms from heavy elements created in stars. Significant dust quantities require substantial stellar processing and multiple generations of stars. Finding dusty galaxies in the very early universe compounds the timeline problem. Not only must these galaxies have formed large stellar populations quickly, they must also have produced and dispersed substantial amounts of heavy elements to create observed dust quantities. Observations of distant quasars, incredibly luminous objects powered by supermassive black holes, reveal similar puzzles. Quasars are among the brightest objects in the universe, with some outshining entire galaxies. The light comes from accretion disks, swirling maelstroms of superheated matter spiraling into central black holes. Webb and other telescopes have detected quasars at enormous distances, corresponding to times when the universe was less than 700 million years old. These ancient quasars present multiple challenges. First, they require supermassive black holes, raising the growth timeline problem discussed earlier. Second, they require vast amounts of gas to feed the black hole and power the observed luminosity. Where did all this gas come from? Third, Quasars exert tremendous influence on their host galaxies through powerful winds and radiation pressure. This feedback can heat and expel gas, suppressing star formation. Yet somehow, these early systems assembled both supermassive black holes and substantial stellar populations. The relationship between black holes and their host galaxies adds intrigue. In the modern universe, a tight correlation exists between central black hole mass and various galaxy properties, particularly the velocity dispersion of stars in the galactic bulge. This relationship suggests black holes and galaxies co-evolve, influencing each other's development through complex feedback mechanisms. But which forms first? Does the galaxy form, then build a black hole at its center? Or does the black hole form first, influencing subsequent galaxy assembly? Webb's observations of the early universe might help answer this chicken and egg question. By studying the properties of high redshift galaxies and their central black holes, astronomers hope to understand the sequence of events during cosmic dawn. Some observations suggest black holes in early galaxies are disproportionately massive compared to their host galaxies' stellar masses. If confirmed, this would indicate black holes formed or grew more rapidly than their host galaxies in the early universe, a pattern quite different from what we observe locally. This raises fascinating questions about black hole formation mechanisms. The traditional scenario involves massive stars collapsing at the end of their lives, creating stellar mass black holes of perhaps 10 to 100 solar masses. But alternative pathways might have operated in the early universe. Perhaps dense star clusters in galaxy centers collapsed directly into intermediate mass black holes of thousands of solar masses. Or maybe primordial gas clouds collapsed directly into massive seeds without forming stars first, a process called direct collapse. Direct collapse scenarios require very specific conditions. The gas must remain hot enough to avoid fragmenting into individual stars, yet dense enough for gravity to overcome pressure and trigger collapse. This balance is delicate, potentially requiring intense ultraviolet radiation to heat the gas while preventing cooling. Some models suggest that radiation from the first generation of stars created conditions favorable for direct collapse in nearby regions, seeding the formation of massive black holes that could then grow into the supermassive monsters we observe. Yet another possibility involves primordial black holes, hypothetical objects that might have formed in the extremely early universe, perhaps in the first second after the Big Bang. If conditions during cosmic inflation or the subsequent hot dense phase allowed certain regions to become sufficiently overdense, they might have collapsed directly into black holes. These primordial black holes could range from tiny masses to potentially thousands or millions of solar masses, providing ready-made seeds for supermassive black hole growth. However, primordial black holes remain entirely theoretical. No definitive evidence for their existence has been found, though they remain candidates for explaining dark matter. If primordial black holes of sufficient mass existed, they could help explain how supermassive black holes appeared so early in cosmic history. But invoking them to solve one mystery requires accepting another entity we haven't confirmed exists, an approach scientists prefer to avoid when possible. The cosmic web adds yet another dimension to these puzzles. Computer simulations reveal that dark matter doesn't distribute uniformly, but instead forms an intricate network of filaments connecting dense nodes. This cosmic web structure emerges naturally from gravitational instability as the universe evolves. Matter flows along filaments toward intersections, where it accumulates to form galaxy clusters. Observations of the modern universe confirm this predicted structure. Galaxies aren't randomly scattered, but instead trace filaments and sheets surrounding vast empty voids. Webb's observations now reveal that this cosmic web structure already existed in surprisingly well-developed form during the universe's first billion years. Distant galaxies appear to align along filamentary structures, suggesting the web assembled much more rapidly than standard models predict. If matter already organized into the cosmic web pattern by 700 million years after the Big Bang, the underlying dark matter structure must have formed even earlier, during the so-called Dark Ages before the first stars ignited. The Dark Ages represent a fascinating but observationally challenging period. After the universe became transparent at 380,000 years, releasing the cosmic microwave background, it entered a period with no light sources. The primordial hydrogen and helium gas filled space, but no stars yet existed to illuminate it. This darkness persisted until the first stars formed, their ultraviolet radiation beginning to ionize surrounding hydrogen in expanding bubbles. This process, called Reionization, transformed the universe from neutral to ionized over several hundred million years. Understanding Reionization is crucial for interpreting Webb's observations. The timing and nature of Reionization depend on properties of the first stars and galaxies. More numerous or more luminous early sources would complete Reionization faster. Observations suggest Reionization finished by roughly 1 billion years after the Big Bang, but the process's details remain uncertain. Webb's ability to observe galaxies during Reionization offers unprecedented opportunities to study this transformation directly. Interestingly, some Webb observations suggest Reionization might have proceeded differently than expected. Certain regions appear to have Reionized earlier than models predict, while others remain neutral longer. This patchy Reionization pattern makes sense in principle. Regions with more early galaxies would ionize first, with ionized bubbles gradually expanding and merging. But the observed patchiness appears more extreme than simulations predict, again suggesting more vigorous early galaxy formation than models anticipate. The abundance of ionizing photons presents another quantitative challenge. Reionizing the entire universe requires an enormous number of ultraviolet photons to strip electrons from every hydrogen atom in cosmic space. These photons must come from early stars and possibly from accreting black holes. Calculating the required photon production rate and comparing it to observed galaxy populations reveals a potential shortfall. The galaxies we see might not produce enough ionizing radiation to explain the reionization timeline inferred from other observations. This photon budget crisis might resolve several ways. Perhaps many small, faint galaxies exist below Webb's detection limits, collectively contributing substantial ionizing radiation. Or maybe the typical early galaxy produced ionizing photons more efficiently than contemporary galaxies, either through a top-heavy initial mass function or through lower dust obscuration, allowing more ultraviolet light to escape. Alternatively, accreting black holes might contribute more to the ionizing background than usually assumed. Each potential solution carries implications. If numerous faint galaxies exist below current detection thresholds, upcoming deeper observations should reveal them. If early galaxies were intrinsically better ionizing photon producers, we need to understand why their properties differed from later galaxies. If black holes play a major role, we need to understand how they became so abundant so early. Ongoing observations and analysis aim to distinguish among these possibilities. Gravitational lensing provides another powerful tool for studying the early universe. Massive objects like galaxy clusters warp space-time, bending light from background objects and magnifying distant sources. Einstein predicted this effect, and astronomers now routinely exploit it to observe objects too faint or distant to detect otherwise. Webb's exquisite sensitivity combined with gravitational lensing allows detection of some of the universe's most distant and faint galaxies. Several of Webb's most remarkable discoveries involve lensed galaxies. The magnification from foreground clusters boosts faint background galaxies into detectability, while also stretching their images, allowing detailed study of internal structure. Some lensed galaxies appear as multiple images around the cluster, with light taking different paths and thus arriving at different times. By analyzing these multiple images, astronomers can reconstruct the background galaxy's properties and also study the lensing cluster's mass distribution. Among the most intriguing lensed objects are extremely red sources that appear as small, compact dots. Initial analysis struggled to determine whether these objects were dusty, star-forming galaxies or something else entirely. Recent work, published in early 2026, reveals many of these enigmatic red dots are heavily obscured glowing black holes. The red color comes from dust absorbing shorter wavelengths, leaving primarily infrared light to escape. The compactness indicates the light originates from a small region, consistent with an accretion disk around a black hole rather than a diffuse galaxy. These dust-enshrouded black holes apparently represent a common but previously hidden phase of early galaxy evolution. The black holes are growing rapidly, possibly at or even exceeding the theoretical Eddington limit. Such vigorous growth might explain how black holes reached supermassive proportions so quickly. If black holes spend a significant fraction of their early existence in heavily obscured phases, growing rapidly while hidden from optical view, they could accumulate mass faster than previously thought possible. The discovery also explains a long-standing puzzle about supermassive black hole demographics. Simulations predict certain numbers of intermediate mass and growing black holes should exist, but observations found fewer than expected. Perhaps they were there all along, hidden behind dust cocoons that earlier infrared telescopes couldn't penetrate adequately. Webb's superior infrared capabilities finally reveal this hidden population, resolving the discrepancy between theory and observation. These findings highlight an important point about astronomical discovery. What we observe depends critically on our instrument's capabilities and wavelength coverage. Each new telescope doesn't just see fainter or more distant versions of known object types, it often reveals entirely new phenomena previously hidden from view. Hubble revolutionized our understanding by observing in optical and ultraviolet light with unprecedented clarity. Webb is now doing the same for the infrared universe, uncovering objects and processes invisible to earlier generations of telescopes. This pattern extends throughout astronomy's history. Radio telescopes revealed pulsars, quasars, and the cosmic microwave background, phenomena invisible to optical telescopes. X-ray observatories discovered neutron stars, black hole binary systems, and hot gas in galaxy clusters. Gamma-ray satellites detected explosive events across the cosmos. Each new wavelength window revealed unexpected aspects of the universe, forcing theoretical revisions and expanding our cosmic perspective. Webb continues this tradition, but with a twist. Rather than opening an entirely new wavelength window, it observes wavelengths accessible to earlier infrared telescopes, but with far greater sensitivity and resolution. This improvement in capability is so dramatic that it effectively functions as a new window, revealing phenomena previous infrared instruments could only hint at or miss entirely. The difference between Webb and earlier infrared telescopes resembles the difference between a magnifying glass and a powerful microscope. Consider the engineering marvel that makes Webb possible. Its primary mirror spans 21.3 feet across, composed of 18 hexagonal segments that unfold after launch. Each segment is coated with an ultra-thin layer of gold, optimized for reflecting infrared light. The mirror must maintain its precise shape despite temperature variations, requiring incredibly sophisticated control systems. The entire observatory operates at approximately -370 degrees Fahrenheit, necessary for detecting faint infrared signals without being overwhelmed by the telescope's own thermal emission. Achieving these frigid temperatures requires a tennis court-sized sunshield, 5 layers of specialized material that blocks heat and light from the sun, earth, and moon. The sunshield maintains a temperature difference of approximately 600 degrees between its sun-facing and space-facing sides. This passive cooling system combined with active refrigeration for certain instruments, creates an observing platform cold enough to detect the infrared whispers from cosmic dawn. Webb's location also contributes to its capabilities. Rather than orbiting Earth like Hubble, Webb resides at a point called the second Lagrange point, or L2, approximately 1 million miles from Earth in the direction away from the Sun. At this location, the gravitational pulls of the Sun and Earth balance in a way that allows Webb to orbit the Sun in sync with Earth while requiring minimal fuel to maintain position. L2 provides a stable, cold environment with unobstructed views of deep space. The scientific instruments aboard Webb represent decades of development. The Near-Infrared Camera, or NER-CAM, serves as the primary imager, capturing stunning pictures across several infrared wavelengths. The Near-Infrared Spectrograph, NIR-SPEC, analyzes light from up to 100 objects simultaneously, determining their compositions, temperatures, and velocities. The mid-infrared instrument, MIRI, extends observations to longer wavelengths, studying cooler objects and dust. The near-infrared imager and slitless spectrograph, NIRIS, specializes in exoplanet atmospheres and wide-field surveys. These instruments work together to provide comprehensive views of cosmic targets. A typical observation might begin with near-cam images to identify interesting objects, followed by near-spec observations to determine their properties and distances, supplemented by MIRI data to characterize dust and cooler components. This multi-instrument approach yields far more information than any single measurement, allowing astronomers to build detailed pictures of distant objects and phenomena. The data volume Webb produces is staggering. Every day, it generates approximately 57 gigabytes of data, transmitted to Earth via NASA's Deep Space Network. This information flows to the Space Telescope Science Institute in Baltimore, where it's processed, calibrated, and archived. Astronomers worldwide access this archive, searching for new discoveries or studying specific objects in detail. Much of Webb's most exciting science comes not from the original observer, but from subsequent researchers mining archival data with fresh perspectives or techniques. This open data policy reflects astronomy's collaborative nature. Unlike some scientific fields where data remains proprietary for extended periods, astronomy generally makes observations publicly available after at most 1 year. This approach accelerates discovery and prevents duplication of effort. It also democratizes access, allowing researchers at institutions worldwide, including those with limited telescope access, to participate in cutting-edge science. Some of Webb's most significant findings have emerged from archival studies by researchers not involved in the original observations. The pace of discovery has been breathtaking. Within Webb's first year of operations, astronomers published hundreds of papers based on its data, spanning topics from our solar system to the most distant reaches of the cosmos. These publications reveal exoplanet atmospheres, stellar birth and death, galaxy evolution, supermassive black holes, and the universe's large-scale structure. Each finding contributes another piece to the cosmic puzzle, and many raise new questions while answering old ones. This brings us back to the central mystery. Why does the early universe appear so different from theoretical predictions? Multiple lines of evidence now point to the same conclusion. Galaxies formed earlier, grew faster, and became more complex than standard models anticipate. Black holes reached enormous masses more quickly than growth rate calculations suggest possible. Large-scale structures assembled with surprising rapidity. Chemical enrichment proceeded more swiftly than stellar evolution timescales seem to allow. These aren't minor discrepancies or isolated anomalies. They represent systematic differences between observation and theory across multiple phenomena. When one observation contradicts theory, we might question the observation or look for special circumstances. When numerous independent observations all point in the same direction, we must seriously consider that our theoretical framework requires modification. We're approaching, or perhaps have already reached, that point with early universe observations. Several broad categories of potential explanations exist. First, our understanding of structure formation physics might be incomplete. Perhaps processes we've neglected or underestimated play crucial roles in the early universe. Second, our cosmological parameters might need adjustment. The values we assign to properties like dark matter abundance, expansion rate, or initial density fluctuations might be slightly wrong, and small changes could have large cumulative effects. Third, new physics beyond our current standard models might operate, particularly at the extreme conditions present in the very early universe. Let's explore each possibility. Regarding structure formation physics, our models necessarily simplify enormously complex processes. Real galaxies involve gravity, gas dynamics, magnetic fields, star formation, stellar feedback, black hole growth, and chemical evolution, all interacting non-linearly across vast scales of space and time. Simulations can't capture every detail, so they use prescriptions and approximations for processes occurring below the resolution limit. If these prescriptions systematically underestimate early structure formation efficiency, they could produce predictions that don't match observations. Star formation provides a key example. The rate at which gas converts into stars depends on local conditions in complex ways. Dense, cold gas forms stars efficiently. Hot, turbulent gas resists collapse. Stellar feedback, through radiation pressure and supernova explosions, can heat and disperse gas, suppressing further star formation. Simulations parameterize these processes using equations calibrated to match observations of contemporary galaxies. But what if early galaxies behaved differently? The early universe's gas had different composition, almost entirely hydrogen and helium, with only trace amounts of heavier elements. This pristine composition affects cooling properties. Interstellar gas cools by radiating energy, and this process depends on which atoms and molecules exist to emit radiation. Pure hydrogen and helium cool less efficiently than gas enriched with carbon, oxygen, and other elements. This should make star formation more difficult in the early universe, yet observations suggest vigorous early star formation. Something must enable efficient cooling despite the lack of metals. One possibility involves molecular hydrogen, designated H2. While atomic hydrogen cools poorly, molecular hydrogen can radiate more effectively. If conditions favored molecular hydrogen formation in the early universe, this might enable efficient cooling and rapid star formation. However, molecular hydrogen is fragile, easily destroyed by ultraviolet radiation. Once the first stars formed and began producing ultraviolet light, they would destroy molecular hydrogen in their vicinity, potentially suppressing further star formation. Understanding this interplay between star formation and feedback in the chemical environment of the early universe remains an active research area. Magnetic fields might also play underappreciated roles. Astronomers detect magnetic fields throughout the universe, from planets and stars to galaxies and galaxy clusters. These fields affect gas dynamics, providing pressure support that can slow gravitational collapse. They also influence how angular momentum redistributes, affecting disk formation and stability. Most simulations include magnetism only crudely, if at all, due to the computational expense of properly solving magnetic field equations. If magnetic fields significantly influenced early structure formation, current simulations might miss important physics. Turbulence represents another poorly understood aspect of cosmic gas dynamics. Interstellar gas isn't smooth and uniform, but instead exhibits chaotic motions across many scales. This turbulence affects star formation rates, mixing of chemical elements, and angular momentum transport. Turbulence also makes simulations computationally expensive, as capturing turbulent motions requires fine spatial resolution. Many simulations treat turbulence approximately rather than resolving it directly. If turbulence behaved differently in the early universe's denser, hotter environment, this could affect galaxy formation in ways current models don't capture. Dark matter's properties provide another avenue for potential modification. The standard cold dark matter paradigm assumes dark matter particles move slowly compared to light speed and interact only through gravity. This framework successfully explains many observations, from galaxy rotation curves to the cosmic microwave background's detailed structure. However, we still don't know what dark matter actually is. Dozens of particle candidates exist, each with slightly different properties that might affect structure formation details. For instance, if dark matter particles have non-zero interaction cross-sections with each other, this self-interacting dark matter could affect how dark matter halos form and evolve. Collisions between dark matter particles would transfer energy and momentum, potentially preventing the densest concentrations from forming or changing halo shapes. These effects might be subtle in the modern universe, but could be more significant in the early universe's denser conditions, potentially accelerating structure formation through mechanisms not included in standard simulations. Alternatively, dark matter might consist of primordial black holes, as mentioned earlier. If a substantial fraction of dark matter comes in the form of black holes rather than exotic particles, this changes structure formation in fundamental ways. Black holes can merge, growing more massive. They can also capture gas, potentially seeding star formation, or growing into supermassive black holes more efficiently than stellar remnant seeds. A primordial black hole component to dark matter could help explain rapid, supermassive black hole growth and possibly accelerate galaxy formation. Cosmological parameter adjustments offer another class of solutions. Our understanding of the universe's composition and history depends on measuring numerous quantities: the current expansion rate called the Hubble constant, the density of ordinary matter, the density of dark matter, the density of dark energy, the amplitude of primordial density fluctuations, and several others. We measure these parameters through various observations, from the cosmic microwave background to distant supernovae to galaxy clustering patterns. Different measurement methods sometimes yield slightly inconsistent results, suggesting either systematic errors in observations or gaps in our theoretical framework. The most notable tension involves the Hubble constant. Local measurements using supernovae and other distance indicators yield values around 73 kilometers per second per megaparsec. Measurements derived from the cosmic microwave background yield approximately 67 kilometers per second per megaparsec. This 6-unit discrepancy might seem small, but it's statistically significant given the precision of modern measurements. This Hubble tension has persisted for years despite intensive efforts to identify errors or systematic effects. If the true Hubble constant differs from the value derived from the cosmic microwave background, this implies our cosmological model needs modification. Various proposals attempt to resolve this tension, from new forms of dark energy to modifications of gravity to additional light particle species. Many of these proposals also affect structure formation predictions, potentially helping explain Webb's observations. For example, if the early universe expanded slightly slower than standard models suggest, this would provide more time for structures to form before reaching a given redshift. An extra 100 or 200 million years might seem modest, but it represents a significant fraction of the available time at high redshift. This additional time could allow more stellar generations to cycle, more gas to cool and collapse, and more mergers to occur, potentially explaining the unexpectedly mature galaxies Webb observes. However, changing expansion history affects numerous observables, not just galaxy formation. Any modified cosmology must remain consistent with the cosmic microwave background's precise measurements, the abundances of light elements produced in Big Bang nucleosynthesis, the distribution of matter on large scales, and many other observations. This requirement tightly constrains possible modifications. Most attempts to resolve one tension create problems elsewhere, a frustrating situation that suggests we might be missing something fundamental rather than just needing small parameter adjustments. New physics beyond the standard models of particle physics and cosmology offers the most radical but potentially most interesting category of solutions. The standard model of particle physics successfully describes matter and forces at accessible energies, tested through countless experiments. The standard cosmological model, lambda-cold dark matter, successfully describes the universe's large-scale evolution. Yet both models contain gaps and puzzles, suggesting they're incomplete. The standard model doesn't include gravity, doesn't explain dark matter's nature, doesn't account for the matter, antimatter asymmetry, and requires unexplained parameter values. The cosmological model includes dark matter and dark energy, mysterious components comprising 95% of the universe's total energy content, yet we don't understand what either actually is. These gaps suggest deeper principles await discovery, unifying currently separate phenomena into more complete theoretical frameworks. String theory represents one attempt at such unification, proposing that fundamental entities aren't point particles but tiny, vibrating strings. Different vibration patterns correspond to different particles, potentially explaining why certain particles exist with particular properties. String theory naturally includes gravity and suggests multiple extraspatial dimensions beyond the three we experience. If true, string theory could provide the mathematical framework for quantum gravity, unifying general relativity and quantum mechanics. However, string theory makes few testable predictions at accessible energies, and the theory admits an enormous number of possible vacuum states, each corresponding to different particle physics and cosmological parameters. This landscape problem makes it difficult to extract definite predictions. Some string theory vacua might permit rapid early structure formation through mechanisms not present in our current effective theories. If we happen to occupy such a vacuum, this could explain Webb's observations. But without a principle selecting which vacuum describes our universe, this explanation remains speculative. Loop quantum gravity offers an alternative approach to quantum gravity, attempting to quantize space-time itself rather than treating it as a smooth continuum. In this framework, space has discrete structure at the Planck scale, approximately 10 to the minus 33 centimeters. This discreteness becomes important only at extreme densities, such as the Big Bang singularity or black hole cores. Loop quantum gravity suggests the Big Bang might actually be a big bounce, a transition from a previous contracting phase to our current expanding phase. If the big bounce scenario is correct, the universe might have existed in some form before the conventional Big Bang, potentially allowing structures to form earlier than standard cosmology permits. Quantum effects near the bounce might also imprint patterns on the distribution of matter that affect subsequent structure formation. These possibilities remain highly speculative, as loop quantum gravity hasn't yet produced a complete cosmological framework comparable to the standard model. Nevertheless, they illustrate how new physics might resolve observational puzzles. Modified gravity theories provide yet another direction. Einstein's general relativity successfully describes gravity across an enormous range of scales and conditions, from laboratory tests to binary pulsars to gravitational wave observations. Yet some cosmological phenomena, particularly dark matter and dark energy, might indicate general relativity requires modification at the largest scales. Numerous modified gravity proposals exist, with varying degrees of success at explaining observations. One class of theories, called scalar tensor theories, adds additional fields to gravity that can affect cosmic expansion and structure formation. Another approach, modified Newtonian dynamics, or M-OND, proposes that gravitational acceleration become stronger than Newton's or Einstein's predictions at extremely low accelerations, potentially explaining galaxy rotation curves without dark matter. While M1D struggles to explain some observations like galaxy cluster dynamics, variants called relativistic MOND or tensor vector scalar gravity attempt to address these issues. If some modified gravity theory correctly describes reality, structure formation might proceed differently than general relativity predicts. Enhanced gravitational attraction at large scales could accelerate structure assembly. Modified expansion history could provide more time for formation. These effects might be subtle in the modern universe but significant during the critical early epochs when galaxies first formed. Testing such theories requires comparing detailed predictions against diverse observations, work that's ongoing for numerous proposed modifications. Beyond these specific frameworks, we must consider the possibility of truly unexpected physics. The history of science reveals numerous instances where new phenomena emerged that no existing theory anticipated. Radioactivity, antimatter, pulsars, gamma-ray bursts, dark energy, and numerous other discoveries surprised researchers, requiring new concepts and frameworks. Perhaps the early universe harbors phenomena we haven't yet imagined, operating under conditions so extreme that qualitatively new physics emerges. This possibility is simultaneously exciting and humbling. Exciting because discovering genuinely new physics represents the ultimate scientific achievement, opening doors to deeper understanding and possibly revolutionary applications. Humbling because it reminds us how much we still don't know, despite centuries of progress. The universe consistently proves more complex and surprising than our theories anticipate. Maintaining intellectual humility while pursuing bold ideas represents science's essential balance. What would genuinely new physics look like? It might involve additional forces acting only under extreme conditions. It could include new particle species that played crucial roles in the early universe, but became irrelevant as conditions evolved. Perhaps quantum effects operate on larger scales than we expect when energy densities reach certain thresholds. Or maybe information theoretic principles we're only beginning to explore place fundamental constraints on how structure can form and evolve. Some theorists propose that consciousness or observation might play roles in physical law, particularly regarding quantum measurement and the transition from quantum superposition to classical definiteness. While these ideas remain highly controversial and speculative, they remind us that the foundations of quantum mechanics still contain unresolved conceptual puzzles. If quantum measurement connects to cosmic structure formation in unexpected ways, this could produce effects we haven't anticipated in our classical-style simulations. Returning to firmer ground, let's consider what additional observations might help resolve these mysteries. Webb continues collecting data, with observations planned for at least the next decade, and potentially beyond if the telescope remains healthy. Each observing program targets specific science questions, from exoplanet atmospheres to stellar evolution to galaxy assembly. Many programs specifically focus on the early universe, attempting to push detection limits to even higher redshifts and fainter luminosities. One key goal involves finding the very first galaxies, corresponding to redshifts perhaps as high as 20 or more, representing the first 200 million years after the Big Bang. These ultra-distant systems should appear extremely faint, requiring Webb's deepest observations in carefully selected regions of sky. Discovering such galaxies would directly reveal when star formation began and how rapidly the first structures assembled. Their properties would test whether the trends Webb observes at slightly lower redshifts extend to even earlier times, or whether galaxy formation transitioned through distinct phases. Another crucial observation program involves spectroscopic follow-up of faint, high redshift candidates. Initial discoveries often come from imaging surveys that detect faint red objects likely at high redshift. However, confirming their distances and measuring their properties requires spectroscopy, splitting their light into component wavelengths to measure precise redshifts and identify atomic and molecular features. Spectroscopy is time-intensive, requiring long exposures on individual objects, but it provides information impossible to obtain from images alone. Webb's spectroscopic capabilities allow detailed studies of early galaxy properties. By measuring emission and absorption lines, astronomers determine which elements are present and in what quantities, revealing chemical enrichment histories. They measure gas temperatures, densities, and velocities, probing physical conditions and dynamics. They identify whether active galactic nuclei, powered by accreting black holes, contribute to observed light. Each spectrum adds constraints to models of galaxy formation and evolution. Particularly exciting are prospects for detecting spectral signatures from population 3 stars, the hypothetical first stellar generation. These stars, if they existed, should have distinctive spectra due to their pure hydrogen-helium composition and extremely high temperatures. Certain emission line ratios would differ from later stellar populations, potentially allowing identification even in integrated galaxy spectra. Several research groups are developing techniques to recognize these signatures, applying them to Webb spectra of high redshift galaxies. Complementary observations from other facilities provide crucial context. The Atacama Large Millimeter Array, or ALMA, observes at millimeter and submillimeter wavelengths, detecting emission from dust, molecular gas, and certain atomic lines. ALMA observations reveal the cold gas reservoirs from which stars form and trace the interstellar medium's physical conditions. Combining Webb's infrared observations with ALMA's millimeter data provides a more complete picture of galaxy properties. Ground-based optical and near-infrared telescopes contribute through wide-area surveys that identify high redshift candidates for detailed follow-up. Facilities like the Subaru Telescope, the European Southern Observatory's Very Large Telescope, and the twin Keck telescopes conduct surveys covering much larger sky areas than Webb, identifying interesting targets. They also provide spectroscopic observations in wavelength ranges Webb doesn't cover, filling gaps in spectral coverage. Future missions will further revolutionize our view. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, will conduct wide-area infrared surveys, discovering many more high redshift galaxies than Webb's targeted observations can find. Roman's field of view is approximately 100 times larger than Webb's, allowing efficient surveys of large sky regions. This wide-area capability complements Webb's deep targeted observations, together providing comprehensive views of early galaxy populations. The European Space Agency's Euclid mission, launched in 2023, surveys billions of galaxies to map dark matter distribution and measure cosmic expansion history. While primarily focused on lower redshifts than Webb, Euclid's wide-area infrared observations will discover numerous high redshift galaxies as byproducts. These discoveries feed into broader studies of galaxy evolution and structure formation, connecting early universe observations to later cosmic epochs. Ground-based extremely large telescopes currently under construction will provide unprecedented light-gathering power and resolution. The Extremely Large Telescope in Chile, with a primary mirror approximately 128 feet across, will be the world's largest optical telescope when completed. The Giant Magellan Telescope and 30-meter telescope, also under construction, will offer similar capabilities. These facilities will conduct spectroscopic studies of faint, high redshift objects with efficiency and detail impossible for current telescopes. Gravitational wave observations add another dimension, the Laser Interferometer, Gravitational Wave Observatory, or LIGO, and its international partners detect ripples in spacetime from colliding black holes and neutron stars. Future space-based gravitational wave detectors like LISA the laser interferometer space antenna will observe lower-frequency gravitational waves from supermassive black hole mergers. These observations directly probe black hole populations across cosmic time, revealing when and how supermassive black holes formed and grew. If supermassive black holes were common in the early universe, as Webb's observations suggest, LISA should detect gravitational waves from their mergers. The rate and properties of these merger events would constrain black hole formation mechanisms and growth histories. Combining gravitational wave observations with electromagnetic observations from Webb and other telescopes would provide comprehensive views of black hole evolution, testing theories against multiple independent data streams. The cosmic microwave background continues to yield insights through increasingly precise measurements. Ground-based experiments and future satellite missions aim to detect primordial gravitational waves, ripples in spacetime from cosmic inflation. These measurements probe physics at energy scales far beyond particle accelerator capabilities, testing fundamental theories about the universe's first moments. CMB observations also constrain cosmological parameters with exquisite precision, testing whether any modifications to standard cosmology can explain both CMB data and Webb's galaxy observations. Numerical simulations grow ever more sophisticated as computing power increases and physical models improve. Modern cosmological simulations can follow structure formation from the universe's first moments through billions of years of evolution, resolving individual galaxies while capturing the cosmic web's large-scale structure. These simulations incorporate increasingly realistic treatments of gas physics, star formation, stellar feedback, black hole growth, and chemical enrichment. By comparing simulation predictions against observations, researchers identify which physical processes most critically affect outcomes. If simulations including particular physics successfully reproduce observations while those omitting it fail, this indicates the included physics is essential. Iterating between observations and simulations, gradually refining both, drives progress toward comprehensive understanding. Webb's observations provide unprecedented benchmarks for testing simulations of the early universe, pushing models toward greater realism and accuracy. Machine learning and artificial intelligence increasingly assist in analyzing astronomical data. Modern surveys generate data volumes far exceeding human ability to examine individually. Automated algorithms identify interesting objects, classify galaxy types, detect anomalies, and extract patterns from multidimensional datasets. These techniques prove particularly valuable for exploring Webb's archive, potentially discovering rare or unexpected objects that targeted searches might miss. Some researchers apply machine learning to simulations, training neural networks to predict galaxy properties from initial conditions or to interpolate between expensive simulation runs. These learned models enable rapid exploration of parameter space, identifying which physical assumptions most affect predictions. Machine learning also assists in connecting theoretical predictions with observations, accounting for complex selection effects and measurement uncertainties that complicate direct comparisons. Citizen science engages the public in research through projects like Galaxies Zoo, where volunteers classify galaxy morphologies in images. These projects achieve classification accuracy comparable to expert astronomers while processing far larger datasets than professionals could handle alone. Citizen science democratizes research participation and often yields serendipitous discoveries when volunteers notice unusual objects that automated algorithms miss. Several web-based citizen science projects are in development, enabling public participation in cutting-edge discoveries. The sociological dimension of scientific progress deserves consideration. Science advances through collective effort, with researchers building upon prior work, debating interpretations, and gradually converging toward consensus or identifying genuine paradigm shifts requiring new frameworks. This process isn't always smooth or linear, Competing theories coexist, sometimes for decades, until sufficient evidence accumulates to favor one explanation over alternatives. During such periods, scientific discourse can become contentious as proponents defend different viewpoints. Webb's early universe observations currently occupy such a phase. Multiple explanations exist for the unexpectedly massive and mature early galaxies, with proponents of each pointing to supporting evidence while critiquing alternatives. Some researchers favor modifications to cosmological parameters, others emphasize uncertain astrophysical processes. Still others advocate for new physics. This diversity of opinion reflects healthy scientific debate, not confusion or failure. Science advances precisely through this process of proposing ideas, testing them against observations, and refining or rejecting them based on evidence. Historical precedent offers encouragement. Previous apparent contradictions between observation and theory often resolved through better understanding of systematic errors, improved models of complex processes, or occasionally genuine paradigm shifts. The discovery of cosmic acceleration in the late 1990s, revealing dark energy's existence, initially seemed almost impossible to accept. The observations contradicted theoretical prejudices, yet multiple independent studies confirmed the finding, forcing acceptance that the universe's expansion is accelerating due to some mysterious energy component. Dark energy's discovery reminds us that the universe can surprise us profoundly. Before 1998, most cosmologists assumed cosmic expansion was slowing, decelerated by gravitational attraction between matter. The possibility of accelerating expansion seemed physically implausible, requiring negative pressure that no known substance possesses. Yet observations demanded it, and theorists scrambled to develop explanations, from vacuum energy to modified gravity to exotic fields. This experience humbles theoretical prejudices while demonstrating the power of following observational evidence wherever it leads. Webb's observations might herald a similar revolution, or they might ultimately prove explicable within existing frameworks once subtle effects are properly included. Either outcome advances science. If existing theories adequately explain observations after refinement, this validates those theories and extends their applicability. If genuine new physics emerges, this opens exciting frontiers for exploration and deeper understanding. The process of determining which scenario applies drives progress, motivating observations, experiments, and theoretical work. Let's step back and appreciate the broader context. A century ago, humanity didn't know galaxies existed beyond the Milky Way. Edwin Hubble's observations in the 1920s revealed the universe contains countless galaxies extending far beyond our own. His subsequent discovery that distant galaxies recede from us at speeds proportional to their distances demonstrated cosmic expansion, establishing that the universe has a history, a beginning, and an evolution. These revolutionary discoveries emerged less than 100 years ago. Just decades earlier, we didn't understand what powered stars or know the sun's age. Lord Kelvin calculated in the late 1800s that gravitational contraction could power the sun for only about 20 million years, creating apparent conflict with geological evidence for an older Earth. This puzzle resolved only with the discovery of nuclear fusion in the 1930s, revealing the energy source enabling stars to shine for billions of years. Our understanding of stellar physics, fundamental to comprehending galaxies and cosmic evolution, developed within the last century. The cosmic microwave background radiation, crucial evidence for the Big Bang theory, was discovered accidentally in 1965 by Arno Penzias and Robert Wilson. They detected mysterious microwave noise in their radio antenna and eventually realized it came from the entire sky, representing thermal radiation from the early universe. This discovery transformed cosmology from largely speculative philosophy into an observational science with testable predictions. The detailed CMB measurements that now precisely constrain cosmological parameters emerged only in recent decades. Dark matter's existence, now widely accepted as explaining galaxy rotation curves and structure formation, was proposed by Fritz Zwicky in 1933 based on galaxy cluster observations, but remained controversial for decades. Only in the 1970s and 80s did compelling evidence from multiple sources establish that dark matter constitutes most cosmic matter. We still don't know what dark matter is, nearly a century after its initial proposal. This reminds us that gaps in understanding can persist for extended periods before resolution. Exoplanets, planets orbiting other stars, remained hypothetical until the first confirmed detections in the early 1990s. Now we know planets are ubiquitous, with most stars hosting planetary systems. The Kepler mission revealed thousands of exoplanets, establishing statistical properties of planetary populations. Webb now characterizes exoplanet atmospheres, detecting molecules that might indicate habitability or even biological activity. This field progressed from 0 confirmed planets to detailed atmospheric characterization in just 3 decades. These examples illustrate how rapidly astronomical knowledge advances when new observational capabilities emerge. Each major telescope or detector opens new discovery space, revealing phenomena previous instruments couldn't access. The pace of discovery often exceeds theorists' ability to develop comprehensive explanatory frameworks, creating temporary tensions between observation and theory. These tensions eventually resolve through combination of better observations, improved theories, and sometimes conceptual revolutions. Webb's current contributions fit this historical pattern. By vastly improving infrared observational capabilities, it reveals phenomena previous telescopes could only glimpse or miss entirely. The unexpected early universe properties it discovers present challenges to existing theories, motivating refinements and possibly fundamental revisions. Whether the resolution involves tweaking parameters, including previously neglected physics, or discovering genuinely new principles, remains to be determined. The process of figuring this out exemplifies science at its best. The philosophical implications of these discoveries warrant reflection. Humanity occupies no special position in space or time. The Copernican principle, the idea that we're not privileged observers, has guided scientific thinking for centuries. Earth isn't the center of the solar system. The solar system isn't the center of the galaxy. The Milky Way isn't the center of the universe. Indeed, the universe has no center, as all locations experience equivalent cosmic expansion. Each successful application of the Copernican principle reveals our cosmic ordinariness. Yet we exist at a particular time in cosmic history. The universe is currently approximately 13.8 billion years old. Stars will continue forming for trillions of years as gas supplies last. Most stars that will ever exist haven't yet been born. Most planets that will ever form don't yet exist. From this perspective, we live in the early universe, witnessing a brief epoch in an enormously longer history. Future observers, trillions of years hence, will inhabit a vastly different cosmos, with structure formation essentially complete and the universe settling into a long, slow fade-out as stars exhaust fuel supplies. Conversely, we observe the ancient universe using light that traveled for billions of years. When we look at galaxies 13 billion light-years distant, we see them as they existed 13 billion years ago, when the universe was young. Those galaxies, if they still exist, have evolved dramatically in the intervening eons. We can't see their current states, as light showing their present conditions won't reach us for billions of years. This creates a peculiar situation where we directly observe the distant past but can only infer present conditions through models and extrapolation. This observational time delay means we study cosmic history rather than the current universe beyond our immediate neighborhood. The early universe isn't somewhere we can visit or interact with. It's a historical epoch we investigate through light that departed long ago. In this sense, astronomy resembles archaeology or paleontology more than experimental physics. We examine records of past events, inferring processes and conditions from preserved evidence. Unlike experimentalists who can manipulate variables, astronomers observe what nature provides, seeking patterns and testing theories against diverse phenomena. The earliest moments we can observe, corresponding to roughly 380,000 years after the Big Bang, when the cosmic microwave background originated, represent an informational horizon. Before that time, the universe was opaque to light, a glowing plasma with photons constantly scattering off free electrons. This opacity prevents direct optical observation of earlier epochs. The CMB represents the oldest light we can see, a baby picture of the universe at approximately 1/40,000th its current age. However, other messengers might eventually reveal earlier times. Gravitational waves propagate freely through matter and radiation, unimpeded by the early universe's opacity. Primordial gravitational waves from cosmic inflation, if detected, would probe physics at energy scales far exceeding any particle accelerator, potentially fractions of a second after the Big Bang. Neutrinos, nearly massless particles that barely interact with matter, should form a cosmic neutrino background analogous to the CMB but originating even earlier, roughly 1 second after the Big Bang. Detecting the cosmic neutrino background presents immense experimental challenges due to neutrinos' weak interactions. No current technology can detect these extremely low-energy primordial neutrinos, but future advances might enable it. Such detection would open another window into the universe's first moments, testing predictions about early thermal history and particle physics at high energies. Each new messenger, light, gravitational waves, neutrinos, potentially others, extends our observational reach and reveals previously hidden aspects of cosmic history. The quantum nature of the very early universe raises profound questions about the meaning of cosmic history. According to quantum mechanics, unobserved systems exist in superpositions of multiple states simultaneously. Only upon measurement does a system assume definite properties. In the early universe, no observers existed to measure anything. Does it even make sense to ask what definitively happened? Or did the early universe exist in quantum superposition until sufficiently complex structures emerged to function as observers? These questions venture into quantum cosmology, an attempt to apply quantum mechanics to the universe as a whole. Unlike quantum mechanics applied to particles or small systems within the universe, quantum cosmology confronts conceptual puzzles about the meaning of wave functions and measurement when no external observer exists. Various interpretations of quantum mechanics offer different perspectives, from many worlds' views where all quantum possibilities realize in branching universes to decoherence approaches where interactions with the environment suppress quantum effects at macroscopic scales. The quantum to classical transition, how definite classical reality emerges from quantum fuzziness, remains philosophically and technically challenging. For most practical purposes, astronomers treat the early universe classically as if it possessed definite properties even when unobserved. This approximation works well for describing structure formation and cosmic evolution. Yet the universe's first instance, when quantum fluctuations dominated and everything existed in an incredibly tiny volume, surely demand full quantum treatment. Understanding this epoch represents one of theoretical physics' grand challenges. Cosmic inflation, proposed in the 1980s, attempts to explain several puzzles about the universe's large-scale properties. Why is space so geometrically flat? Why is the cosmic microwave background temperature nearly identical in all directions, even in regions that seem never to have been in causal contact? Inflation proposes that the universe underwent exponential expansion during an incredibly brief period, perhaps from 10 to the minus 36 seconds to 10 to the minus 32 seconds after the Big Bang. This expansion stretched the universe from subatomic scales to macroscopic sizes. During inflation, quantum fluctuations in the inflaton field, the hypothetical field driving inflation, stretched to macroscopic scales, becoming the seeds of all cosmic structure. These quantum ripples, frozen into classical density variations, provided the initial conditions from which galaxies and large-scale structures eventually formed. This connection between quantum physics and cosmic architecture beautifully unifies microscopic and macroscopic realms, suggesting that the universe's largest structures originate from quantum uncertainty. Inflation makes testable predictions about the statistical properties of density fluctuations, predictions confirmed by cosmic microwave background observations. The fluctuations should be nearly scale invariant, meaning similar amplitudes at different scales, with slight deviations characterized by spectral indices that inflation predicts. Observations match these predictions remarkably well, providing strong circumstantial evidence for inflation. However, direct evidence, particularly detection of primordial gravitational waves from inflation, remains elusive despite intensive searches. The failure so far to detect primordial gravitational waves doesn't disprove inflation but constrains which versions of the theory describe reality. Different inflaton potentials, the functions describing the inflaton field's energy density, predict different gravitational wave amplitudes. High-energy inflation models predict strong gravitational wave signatures, while low-energy models predict weaker signals, possibly beyond current detection capabilities. Continuing improvements in CMB polarization measurements gradually tighten constraints, eliminating some inflationary models while preserving others. Alternative scenarios to inflation exist, attempting to explain the same observational features through different mechanisms. Bouncing cosmologies propose that the universe contracted from a previous phase, bounced at some minimal size, then began expanding. Cyclic models envision infinite sequences of expansions and contractions. These alternatives face theoretical challenges and generally make predictions less consistent with observations than inflation. Nevertheless, they remind us that inflation, despite its successes, isn't proven beyond doubt. Science requires maintaining some skepticism even toward highly successful theories. Returning to Webb's observations and their implications, we see how discoveries about galaxy formation connect to fundamental questions about cosmic origins. The properties of the first galaxies depend on initial conditions set during inflation, modified by subsequent evolution through the Dark Ages and Reionization. Understanding this causal chain from quantum fluctuations to galaxy formation represents a grand synthesis spanning physics from the smallest to largest scales. If early galaxies formed faster than models predict, this might trace back to properties of primordial fluctuations. Perhaps the fluctuation spectrum differs slightly from simple inflation predictions in ways that enhance structure formation. Or maybe inflation occurred at higher energies than typically assumed, producing stronger fluctuations that seed earlier galaxy formation. These possibilities connect observational cosmology with fundamental physics in exciting ways. The nature of dark energy adds another layer of uncertainty to cosmic evolution. Dark energy's density appears nearly constant over time, acting as a cosmological constant in Einstein's equations. This simplest possibility, represented by the Greek letter lambda in the lambda cold dark matter model, matches observations reasonably well. However, alternatives where dark energy density evolves over time remain viable. Such quintessence models might affect structure formation differently than a cosmological constant, potentially altering predictions for galaxy assembly. If dark energy density was lower in the early universe, gravitational attraction would have been relatively stronger, potentially accelerating structure formation. Conversely, if dark energy was higher, this would impede structure growth. Observational constraints on dark energy's evolution come primarily from supernova distances and galaxy clustering at different redshifts. Webb's observations of early galaxies provide another constraint, as galaxy abundances and properties depend on cosmic expansion history. Combining multiple independent constraints gradually narrows the range of allowed dark energy behaviors. The coincidence problem surrounding dark energy raises philosophical questions. Dark energy's density is similar to matter's density today, despite their different evolution over cosmic history. Matter density decreases as the universe expands, diluting as volume increases. Dark energy density, if truly constant, remains unchanged despite expansion. In the past, matter dominated. In the future, dark energy will dominate ever more overwhelmingly. We happen to live during the brief transition epoch when they're comparable. Is this timing coincidental, or does it suggest some connection between dark energy and matter? Various anthropic arguments attempt to explain this coincidence. Perhaps intelligent observers can only emerge during epochs when structure formation has produced galaxies and stars, but dark energy hasn't yet dispersed everything beyond observable horizons. From this perspective, we necessarily observe dark energy and matter with similar densities because we couldn't exist otherwise. Such reasoning proves controversial, as it invokes observer selection effects rather than dynamical explanations. Yet, if the multiverse contains regions with different dark energy densities, anthropic selection might genuinely explain our observed value. The multiverse concept itself remains highly speculative, but emerges naturally from several theoretical frameworks. Eternal inflation suggests that inflation never completely ends everywhere, but continues eternally in some regions while stopping in others, creating infinite bubble universes with potentially different physical properties. String theory's landscape of possible vacuum states suggests different regions might realize different vacua with different particle physics and cosmological parameters. If the multiverse exists, what we call the universe is merely our local bubble, one among countless others. Testing multiverse ideas presents profound challenges. By definition, other universe regions lie beyond our observational reach, causally disconnected by exponential expansion or existing in separate space-time structures. Some researchers suggest that bubble collisions might leave detectable imprints on our cosmic microwave background, offering indirect evidence for the multiverse. Others propose that the distribution of observed physical constants might statistically favor anthropic selection from a landscape. These ideas remain controversial and largely unfalsifiable by conventional criteria. Whether or not the multiverse exists, we must explain our universe's properties using physics accessible to observation and experiment. Webb's discoveries about early galaxy formation demand explanation in terms of physical processes operating within our cosmic horizon. The challenge for theorists is developing models consistent with these observations while remaining compatible with other constraints from the cosmic microwave background, Big Bang nucleosynthesis, large-scale structure, and fundamental physics. One intriguing possibility involves feedback between different cosmic components. Perhaps early black hole growth affected galaxy formation more strongly than current models assume. Black holes accrete gas, releasing tremendous energy that heats surrounding material. This feedback can suppress star formation by preventing gas from cooling and collapsing. However, the energy injection might also compress gas in certain regions, triggering star formation. The balance between suppression and triggering depends on detailed physical conditions and geometries. If early black holes formed rapidly and grew vigorously, as Webb observations suggest, their feedback effects might have profoundly influenced galaxy assembly. Perhaps this feedback actually accelerated galaxy formation in some environments, contrary to usual assumptions. Or maybe the black holes formed within already massive galaxies as effects rather than causes of rapid structure formation. Disentangling causation from correlation requires detailed observations of many systems at different evolutionary stages. The role of environment in early galaxy formation deserves attention. Not all regions of the early universe were equivalent. Density varied from place to place due to primordial fluctuations. Overdense regions containing more matter than average experienced stronger gravitational pull and collapsed earlier. Underdense regions, the voids between structures, remained relatively empty as matter drained toward overdensities. This hierarchical structure formation paradigm predicts that galaxies formed first in the densest environments, then gradually in less dense regions. Webb observes galaxies in various environments, from relative isolation to dense protoclusters, the progenitors of modern galaxy clusters. Comparing galaxy properties across environments tests whether early galaxy formation depended on local density in expected ways. If all galaxies appear similarly mature regardless of environment, this challenges hierarchical formation models. If environmental differences appear as predicted, this supports standard structure formation while requiring explanation for why galaxies everywhere formed earlier than anticipated. Protocluster observations prove particularly interesting. Modern galaxy clusters are the universe's largest gravitationally bound structures, containing hundreds or thousands of galaxies within regions a few million light-years across. Clusters form at the intersections of cosmic web filaments, where matter accumulates over billions of years. Protoclusters represent early stages of this process, overdense regions destined to become clusters but not yet fully collapsed. Webb detects protoclusters at high redshift, revealing how these structures assembled. Some protoclusters appear remarkably well developed by surprisingly early times, containing numerous massive galaxies in close proximity. The total stellar mass in these regions challenges theoretical predictions for how rapidly matter could accumulate and form stars. If protoclusters already contained substantial stellar populations less than 1 billion years after the Big Bang, the underlying dark matter halos must have assembled even earlier. This timeline pressure compounds the difficulties standard models face in explaining Webb's observations. Galaxy morphologies provide additional clues about formation processes. Modern galaxies exhibit diverse shapes: spiral galaxies with rotating disks and spiral arms, elliptical galaxies with smooth spheroidal shapes, irregular galaxies lacking organized structure. These morphologies reflect formation histories. Spirals typically form through gradual gas accretion onto rotating disks with ongoing star formation in spiral arms. Ellipticals generally result from major mergers between gas-rich galaxies, violent events that destroy disk structure and trigger intense star formation. Early galaxies observed by Webb show diverse morphologies despite their youth. Some appear as compact, irregular clumps consistent with expectations for actively forming systems. Others display surprisingly regular structures, including possible disk morphologies suggesting organized rotation. A few appear to show multiple components, possibly representing ongoing mergers. This morphological diversity at high redshift indicates that galaxy assembly processes varied, with different systems evolving through different pathways. The existence of organized structures like disks in very early galaxies raises dynamical questions. Disk formation requires that infalling gas conserves angular momentum, settling into a rotating configuration rather than dispersing randomly. Turbulence, mergers, and feedback processes can destroy disks or prevent their formation. Finding disk-like morphologies at high redshift suggests these disruptive processes were less dominant than formation mechanisms enabling organized structures. Understanding what permitted disk survival or formation in the chaotic early universe challenges theorists. Star formation modes in early galaxies might have differed from modern star formation. Contemporary galaxies form stars primarily in giant molecular clouds, dense cold regions where gravity overcomes pressure to trigger collapse. This process is relatively inefficient, with only a few % of available gas converting to stars per cloud's dynamical timescale. Stellar feedback from radiation, winds, and supernovae disperses remaining gas, terminating star formation until gas reaccumulates. Perhaps early galaxies formed stars more efficiently, converting larger gas fractions into stars before feedback intervened. This might occur if gas densities were higher, enabling more rapid collapse, or if feedback was less effective at dispersing gas. Alternatively, star formation might have occurred more continuously rather than in discrete bursts, maintaining high average rates despite similar instantaneous efficiency. Distinguishing these scenarios requires detailed observations of gas properties, star formation rates, and stellar population ages in high redshift galaxies. Stellar population synthesis, the modeling of how stellar populations evolve over time, provides tools for interpreting galaxy observations. Different stellar populations produce characteristic spectra depending on their ages, compositions, and initial mass functions. By comparing observed spectra to models, astronomers infer properties like stellar ages, star formation histories, and chemical abundances. These inferences depend on stellar evolution theory and assumed initial mass functions, introducing uncertainties when conditions differ from modern galaxies. Applying stellar population synthesis to high redshift galaxies requires caution. If early galaxies had top-heavy initial mass functions, standard models assuming modern-day mass distributions would incorrectly infer stellar masses and ages. If stellar evolution proceeded differently in pristine low metallicity environments, age estimates might be systematically wrong. These uncertainties complicate efforts to determine whether observed galaxies are genuinely more massive or mature than models predict, or whether we're misinterpreting observations due to incorrect assumptions. Breaking these degeneracies, the situations where different parameter combinations produce similar observable outcomes, requires multiple independent constraints. Spectroscopy provides some constraints through emission and absorption line strengths. Multi-wavelength photometry, measuring brightness across many filters, constrains spectral energy distributions. Morphological information indicates star formation geometries and dynamical states. Combining these diverse measurements gradually narrows possibilities, converging toward robust conclusions despite individual measurement uncertainties. The role of binary stars and stellar interactions adds complexity to stellar population modeling. In dense early environments, stars might form in tighter clusters with more frequent interactions. Binary evolution, where two stars orbit each other and exchange mass, affects stellar lifetimes and observable properties. Mergers between stars create unusual objects that wouldn't exist in isolation. If stellar interactions were more common in early galaxies, this could affect their integrated properties in ways standard models don't capture. Chemical evolution modeling attempts to track how element abundances change over time as stars form, live, and die. Different elements form through different processes with different timescales. Hydrogen and helium originate in the Big Bang. Carbon, nitrogen, and oxygen form in intermediate mass stars and disperse through stellar winds and planetary nebulae over tens to hundreds of millions of years. Iron group elements form primarily in Type Ia supernovae, explosions of white dwarfs in binary systems, with delay times potentially ranging from tens of millions to billions of years. The observed abundance patterns in high redshift galaxies constrain chemical evolution timescales. If galaxies show substantial iron enrichment, sufficient time must have elapsed for Type Ia supernovae to contribute. If oxygen is abundant but iron scarce, this suggests young stellar populations dominated by massive stars that explode as core collapse supernovae. Measuring detailed abundance ratios through spectroscopy provides a chronometer, revealing how long stellar populations have been evolving. Some high redshift galaxies show abundance patterns suggesting surprisingly mature stellar populations for their cosmic epoch. The presence of substantial iron and other iron peak elements indicates multiple stellar generations have cycled. However, uncertainties in supernova timescales and yields complicate quantitative interpretation. If type Ia supernovae occurred more promptly in early environments, or if their iron yields differed, abundance patterns might not straightforwardly indicate ages. Resolving these ambiguities requires better understanding of stellar evolution and supernova physics in low metallicity environments. Dust formation and destruction processes add another layer of complexity. Cosmic dust forms primarily in stellar atmospheres and supernova egestions, but the efficiency depends on chemical composition and physical conditions. In low metallicity environments, reduced availability of heavy elements might suppress dust formation. Yet some high redshift galaxies show evidence for substantial dust, requiring either efficient dust production or perhaps alternative dust sources like direct condensation from the interstellar medium. Dust affects observations profoundly by absorbing and scattering light, modifying observed spectra and luminosities. Dust-obscured galaxies appear redder and fainter in ultraviolet and optical wavelengths while shining brightly in infrared. Correcting for dust effects requires modeling or observational constraints, introducing uncertainties. If dust properties differed in the early universe, having different grain size distributions or compositions, standard extinction corrections might not apply, potentially leading to systematic errors in inferred galaxy properties. The interstellar medium structure and physics in early galaxies remain poorly understood. Modern galaxies' interstellar medium exhibits complex multi-phase structure with cold, dense molecular clouds, warm neutral medium, warm ionized gas, and hot, shocked gas coexisting. This structure reflects balance between heating sources like stellar radiation and supernova, cooling processes, and dynamical mixing. The early universe's different conditions, higher background temperature, different chemical composition, possibly stronger radiation fields, might produce different interstellar medium structures. Understanding the early interstellar medium matters because it regulates star formation. Stars form in cold, dense gas, so the fraction of gas in cold molecular phase directly affects star formation rates. If early galaxies maintained larger cold gas fractions, this could enable higher star formation rates. Conversely, intense radiation and feedback might have kept more gas hot and diffuse, suppressing star formation. Observations of molecular gas in high redshift galaxies using ALMA and other facilities help constrain interstellar medium properties, though detecting molecular emission from very distant sources challenges even the most sensitive instruments. Cosmic rays, high-energy particles accelerated in supernova remnants and other energetic events, influence the interstellar medium through heating and pressure support. Cosmic ray pressure can puff up galactic disks and drive galactic winds that expel gas. If cosmic ray production rates differed in early galaxies, this could affect their evolution. However, cosmic rays prove difficult to observe directly except locally, so their role in distant galaxies remains largely theoretical, constrained primarily through models rather than direct measurement. Magnetic fields, already mentioned briefly, deserve fuller consideration. Galactic magnetic fields arise through dynamo processes amplifying weak seed fields via turbulent gas motions and differential rotation. These fields affect gas dynamics, provide pressure support, resisting gravitational collapse, and guide cosmic rays. The timescales for building strong magnetic fields through dynamos might be comparable to galaxy ages at high redshift, raising questions about whether early galaxies possessed significant magnetic fields or whether they remained magnetically weak. Some observations suggest surprisingly strong magnetic fields in high redshift galaxies inferred from polarization measurements and synchrotron emission. If confirmed, this indicates either very efficient dynamo amplification or perhaps stronger seed fields than typically assumed. Primordial magnetic fields might have existed in the early universe, generated during phase transitions or inflation, providing stronger starting points for dynamo amplification. Alternatively, turbulence in rapidly forming galaxies might drive exceptionally fast dynamo action. The connection between galaxy properties and their dark matter halos represents a central theme in galaxy formation theory. Dark matter halos form through gravitational collapse of dark matter, creating potential wells into which baryonic matter falls. The halo's mass, shape, and concentration affect how gas accumulates and forms stars. Galaxy properties should correlate with halo properties, relationships that simulations predict, and observations test. One key relationship involves galaxy stellar mass and halo mass. More massive halos should host more massive galaxies, but the relationship isn't one-to-one. Feedback processes prevent all available gas from forming stars, with efficiency varying across halo mass scales. At low masses, supernova feedback efficiently expels gas. At high masses, gravitational potential wells are too deep for supernovae to eject gas, but black hole feedback becomes important. This produces a peak efficiency at intermediate masses, with lower star formation efficiency both below and above this scale. Observations of galaxy stellar mass functions, the number of galaxies per unit volume at different masses, constrain this efficiency. The shape of the stellar mass function reflects the interplay between halo mass distribution and star formation efficiency. Webb's observations of high redshift galaxy mass functions reveal how this relationship evolved over cosmic time. If early galaxies were more abundant at high masses than predicted, this suggests either that massive halos formed earlier or that star formation efficiency was higher than models assume. Halo occupation distribution modeling provides a framework for connecting galaxies to dark matter. This approach statistically describes how many galaxies occupy halos of given masses, distinguishing central galaxies at halo centers from satellite galaxies orbiting within larger halos. By comparing predicted and observed galaxy clustering, astronomers constrain occupation statistics and infer typical halo masses for galaxies of different types. Applying these techniques to high redshift observations helps determine whether early galaxies occupy unusually massive halos. The abundance matching technique offers another approach, monotonically matching galaxy stellar mass ranks to halo mass ranks. This assumes stellar mass correlates with halo mass, even if the exact relationship is uncertain. Abundance matching successfully reproduces many observed correlations in the local universe. Applying it to high redshift observations tests whether similar relationships held at early times or whether the galaxy halo connection evolved. Some evidence suggests the galaxy-halo relationship did evolve, with early galaxies possibly more efficient at converting baryons to stars. If confirmed, this evolution requires physical explanation. Perhaps feedback processes were less effective initially, becoming more efficient as metallicity increased and black holes grew. Or maybe gas accretion onto early halos was more efficient, with higher accretion rates overwhelming feedback. Understanding this evolution connects to broader questions about feedback regulation of galaxy growth. Galactic winds, driven by stellar feedback and black hole activity, represent crucial regulatory mechanisms. Observations detect outflows in local star-forming galaxies and distant quasars, with speeds ranging from hundreds to thousands of kilometers per second. These winds carry mass, energy, and metals out of galaxies, affecting their subsequent evolution. Strong winds can quench star formation by expelling gas, while enriching the circumgalactic medium and intergalactic medium with processed material. Evidence for winds in high redshift galaxies comes from blue-shifted absorption lines indicating outflowing gas, and from spatial extent of certain emission lines showing extended structures. However, characterizing wind properties requires high-quality spectra difficult to obtain for faint distant objects. Webb's spectroscopic capabilities enable better wind studies than previously possible, revealing how feedback operated during the universe's first billion years. Understanding early feedback is crucial for explaining galaxy mass assembly and chemical enrichment timescales. The circumgalactic medium, gas surrounding galaxies beyond stellar regions but within dark matter halos, increasingly interests researchers. This gas reservoir feeds star formation while also receiving feedback-enriched outflows. The cycling of gas between galaxies and their circumgalactic medium, sometimes called the baryon cycle, regulates galaxy evolution. Observations of the circumgalactic medium using absorption spectroscopy, where background light sources illuminate foreground gas, reveal its physical and chemical properties. Studying the circumgalactic medium around high redshift galaxies proves challenging but rewarding. Absorption systems in quasar spectra provide information about intervening gas, but associating absorption features with specific galaxies requires knowing precise redshifts and spatial relationships. When successful, such studies reveal that early circumgalactic media were metal-enriched, indicating substantial stellar processing, and feedback had already occurred. This enrichment provides additional evidence for vigorous early star formation. The intergalactic medium, gas-filling space between galaxies, also carries information about galaxy evolution. Feedback ejects material into intergalactic space, enriching it with metals. The metallicity of intergalactic gas reflects cumulative stellar processing across cosmic history. Additionally, the ionization state of intergalactic hydrogen traces Reionization's progress. Observations of the intergalactic medium using quasar absorption spectroscopy reveal gradual metal enrichment and patchy reionization consistent with galaxy-driven processes. Bringing together all these threads, galaxy masses and ages, black hole growth, chemical enrichment, dust formation, star formation modes, feedback processes, and large-scale structure, paints a complex picture of the early universe. Each piece of evidence constrains possible formation scenarios, gradually narrowing the range of viable explanations for Webb's surprising discoveries. While significant uncertainties remain, the outlines of a resolution are beginning to emerge. The emerging consensus suggests that no single dramatic revision to cosmology or fundamental physics is necessarily required. Instead, multiple astrophysical processes, each individually plausible but collectively more vigorous than standard models assumed, might explain observations. Star formation efficiency was possibly higher initially. Black hole seeding mechanisms might have been more effective. Feedback regulation might have operated differently in pristine environments. Galaxy mergers might have occurred more efficiently in dense early environments. Additionally, observational selection effects and systematic uncertainties might contribute to apparent tensions. The most extreme early galaxies are, by definition, rare and unusual, not necessarily representative of typical populations. Dust obscuration might hide many normal galaxies while preferentially revealing extraordinary ones. Photometric redshift uncertainties might place some objects at incorrect distances, contaminating high redshift samples with lower redshift interlopers. As observations improve and systematic effects are better understood, some apparent anomalies might diminish. Nevertheless, even accounting for selection effects and systematics, Webb's observations genuinely challenge standard models in ways requiring theoretical attention. The preponderance of massive galaxies, the rapid black hole growth, the early chemical enrichment, and the mature morphologies collectively indicate that galaxy formation proceeded more efficiently in the early universe than simulations typically produce. Understanding why remains an active research frontier. Future observations will continue refining our understanding. Deeper surveys will reveal fainter, possibly more typical early galaxies. Spectroscopic follow-up will confirm distances and characterize properties. Multi-wavelength observations will probe gas, dust, and stars comprehensively. Gravitational lensing will enable detailed studies of intrinsically faint objects. Each new dataset adds constraints, gradually converting uncertainty into knowledge. Theoretically, more sophisticated simulations incorporating improved physics and higher resolution will make more realistic predictions. Machine learning techniques will help explore parameter space efficiently. Analytic modeling will provide physical intuition complementing numerical simulations. The interplay between observation and theory, each informing and challenging the other, drives scientific progress toward comprehensive understanding. The broader implications of these discoveries extend beyond galaxy formation. Understanding when and how the first structures assembled connects to fundamental questions about cosmic origins, the nature of dark matter and dark energy, and the physical laws governing the universe. Each discovery about the early universe provides another piece of the cosmic puzzle, gradually revealing the full story of how we came to exist. From quantum fluctuations in the first moments after the Big Bang, through the Dark Ages and cosmic dawn, through the formation of first stars and galaxies, through billions of years of cosmic evolution, this epic story encompasses the grandest scales in space and time. Webb's observations reveal pivotal chapters of this story with unprecedented clarity, inspiring wonder while raising new questions for future generations to explore. As we conclude this exploration of Webb's discoveries and their implications, we recognize that science never truly concludes. Each answer spawns new questions. Each observation reveals new mysteries. The early universe, far from being a solved problem, remains a vibrant research frontier where observation and theory productively clash, driving understanding forward. Josue, what began as a simple yes, has taken us on a journey from the technical specifications of the James Webb Space Telescope through the cosmic history it observes, from galaxy formation, physics, to cosmological principles, from confirmed discoveries to speculative possibilities. This journey reflects science's essence, the endless quest to understand nature through observation, reasoning, and imagination, always seeking deeper truths while remaining grounded in evidence. The universe continues to surprise us, revealing complexity and beauty beyond what theory anticipates. Webb's first years of operation have merely begun uncovering the early universe's secrets. The coming decades promise even more remarkable discoveries as this extraordinary telescope continues observing, as complementary facilities join the effort, and as new generations of scientists bring fresh perspectives to cosmic mysteries. The story of cosmic dawn is still being written, with each observation adding another sentence, each discovery another paragraph. We live in privileged times, witnessing revolutionary advances in humanity's understanding of our cosmic origins and place in the universe. But have you ever wondered what the speed of light really is? The video at the left side of the screen explores why light slows down in materials like water and diamond to 40% vacuum speed, how scientists at Harvard brought light to complete stop in Bose-Einstein condensates in 2001, and why the cosmic speed limit applies to causality and information, not just photons. See you there.